Good afternoon. Very excited to welcome everyone today. We have a real treat especial. Mike Dodds is here up from Portland, where he's a super big deal at Galois, which is a really cool employee-owned company that does all kinds of interesting formal methods and verification work. I think a lot of people have been pretty excited about this talk. If you haven't noticed, there's this thing called AI now that can solve all of computer science, except not always. And so people are pretty nervous about how do we make sure that the code we're getting out of these things is right. And so Mike has thought a lot about that, and I'm really excited to hear more about it. Before we jumped into the talk, a brief background though. I was really excited to have Mike come up. In my classes, we often read papers that are skeptical or nuanced critiques of formal methods. And actually this quarter in my class, 2 of those are from Mike. So it's really nice when you can have somebody who's a shining example leading the field, who's also one of the most thoughtful and nuanced people reflecting on progress as well. So I think that we're all in for a real treat. Let's welcome Mike.
Yeah, thanks very much. Zach. It's funny, what happens is I get annoyed about things and then I write blog posts and they gradually become more and more nuanced. I gradually think about it more and I talk myself into the more nuanced position, but the first drafts are much spicier, so I should probably not publish those. So I'm here from Galois. We're about 110 people, a sort of employee-owned sort of R&D temp agency of sorts. I think people sometimes call these BBNs, they're kind of, we make our way on kind of DARPA contracts and things like that. Mostly doing security, reliability sort of things. And I was a professor, not a very good professor, in the UK from about 2004 to 2017. And since then, I've been a principal at Galois. And it's been an amazing time. My real, the heart of me, my heart belongs to formal verification. But in recent years, I've been more of an AI dabbler. So, moderate any confidence in my opinions accordingly, I would say. So, okay, this is a hot takes talk. So, top level hot take, I think proofs are going to get cheap. And from the beginning of time until this year, proof was a thing that was very, very expensive because humans had to do it with their wet, soft, kind of imperfect brains. And AI has been gradually getting better and better and better. And I think I'm going to call it and say that eventually the AI is going to be quite soon good at proof in a way that means that it's going to be radically cheaper. And this is good because proof technology is very useful. And I think it's probably time, if we care about formal verification, to think quite big about what we do next. So I will now talk about these matters. So the first thing to talk about is AI and trust. And I think that AI presents a whole bunch of really interesting trust problems. So when we use AI, I'm sure that you've all used AI. This is my prototypical AI slide. So you ask an AI a question, and the AI sort of gives you an answer, and it comes to you by some process you don't understand, and then the answer, it turns out it's right or it's wrong. In this case, I don't have a math degree, but I'm pretty sure this one's wrong. So, okay, this is good, because we can tell the answer is wrong. But then we want to ask AI things where we don't know the answer. We want to say, hey, come on, build me a really amazingly secure VPN. And the AI kind of says, the AIs always want to help you. They're very kind of accommodating. And so it's yeah, you know what? OK, fine. Yeah, let's do it. It does some process you don't understand. Something happens. And then it gives you a really, really secure VPN. And it's you're is this secure? And you're yeah, no, it's secure. And then you look at it and you're oh, yeah, OK, this wasn't exactly what I wanted. It's kind of, it steals your passwords, or it kind of exfiltrates your data. And then you're sad and you're OK, probably I shouldn't use AI for critical system stuff. And this isn't a new observation, right? People have known this for a while. So Leopold Aschenbrenner's piece, Situational Awareness, very good kind of early in the sense 2 years ago. But one of the pieces I read early on when I was thinking about AI, it talks about this problem that when the AI is small, it does things that are interpretable. We can see that it's correct. And when it's big, it does stuff, and you're well, is this safe? Is this the I wanted? Well, you just sort of can't tell. So you better kind of hope, right? We'd really like to solve this sort of problem. So ideally, what we'd really want is we really want to say, can you build me this really secure VPN? And you have some way of finding out whether or not you got the thing you wanted. you kind of want to know that your security analysis says that this is secure. This is like, does it use the cryptography correctly? Does the encryption correctly? I mean, really, what you want is the sort of hedonic analysis that says, you got exactly what you wanted. You are satisfied. You are happy. This obviously doesn't happen. I'm English, so it's never going to happen. But it's like you're kind of less unhappy, at least. And so we'd really like to kind of get that. Now, the theme here is that we'd really like to have ways of kind of having the AI be a sort of untrusted source of things and have some other way of like getting to kind of trusted kind of guarantees. And this is like a very kind of nice pattern if we can achieve it. Like, you know, on one side, we want to have like heuristic processes where we kind of search for things. We use any means available. We get kind of quick, you have a quick and powerful and opaque process, and we can sort of like be wrong, and it doesn't matter. Like the AI can be powerful and it doesn't matter. On the other hand, we want ways to check this, which are kind of highly predictable, that are slow and legible. We can be confident that they got things right, where we have guarantees of correctness. And we really would like this because we want, in some cases, the decisions actually matter. I'm going to resist saying the words P and NP in here somewhere. But, you know, this is sort of like a deep kind of like thing in computer science that sometimes we are seeking the answer and sometimes we are checking the answer. And like for AI, we want to kind of do this for lots of kinds of things. We want to know that our theorems, the AI comes up with theorems that it claims are correct. And we want to know that the theorems are true. For AI-built systems, we want to know the AI-built system is secure or safe or correct or the thing you wanted. You know, you are satisfied. AI actions, you want the actions to be allowed or helpful or harmless. And ideally, we want the AI to be mostly not a thing we have to trust. We want to increase the probability we get the answer we want, but we don't want to have to rely on that because these things are giant neural networks. They're more grown than built. You know, they're not things we can trust necessarily. So the good news is that AI is starting to get good at math, and that math might give us tools for kind of getting to this state where we can do like search over, where we can kind of get to trustworthy checks. So AI has been doing sort of math for a while, and I think it's been pretty interesting what's happened. So, I mean, the first bit of news is like AI is quite good. We may have some skeptics in the audience of this claim. I'm happy to argue with afterwards. But AI has clearly got quite a lot better over the last short while. So this is the number one cliche of any AI talk. I'm now going to put up a line on a graph that's going up, and it has time on the bottom. OK. I imagine many of you have seen this graph before. This is the study from an organization called Meta. It's the time horizon graph. And so the way this study works, is that they took a bunch of tasks, and they got humans to do those tasks. And then they measured how long the humans took. And then they measured like what percentage of which of these tasks could the AI do. And so the claim is that like a long task is a more difficult task, I suppose. So what we see here is that early on, GPT-2, we have, GPT-2 can do things that a human could do in 4 seconds. These are not very long tasks, very big tasks. And what we see is a nice kind of like, this is a log scale, so this is an exponential. What we see is Claude Opus 4.6 can do tasks that a human might take 10 hours to do. Like these are quite difficult tasks. And so we see just consistent improvements in the AI's ability to do things that like humans intuitively find difficult. And we also see sometimes quite dramatic jumps in ability. So many of you may have noticed that the new model came out recently. It didn't come out. It wasn't released. It's called Mythos. And so here's something from the AI, the Anthropic red teaming team. So what this is finding JavaScript shell exploits autonomously. And basically, what we see is like Opus 4.6, then the kind of state of the art, just fairly recently released. And that little red line at the bottom there is it can do sort of like, it can construct like 0.3% or something of the kind of cases it can find exploits. And like Mythos, which is like built a couple of months later, it can build exploits in 72% of the cases, right? That's like 100x increase in its ability to build these kind of things. That's quite a large gain in capability. This seems bad. It seems like a thing. It's also true, I think, that AI is starting to get really good at math. And I think that you can see this really clearly in this sort of frontier math benchmark. So frontier math is designed as a benchmark of graduate level math problems. So these are problems where they are designed by mathematicians, they are closed, they're not on the public internet, and they are designed to test AI capabilities. So the tiers are roughly difficulty tiers. Tiers 1 to 3, there's also a tier 4, on here, which I haven't put up here, but it has more or less the same shape. And tiers 1 to 3 are sort of all the way up to, I think, more or less like individual grad level mathematician tasks. So these are quite hard tasks. Like I clearly can't do any of these tasks. And what we see again is between July 2024, most of the models got 0. And then we get to 2026, they're scoring 45%, 50% of these are not repeating things that are in the data set. This is in some sense, brand new knowledge because there's no way the model could have found it other than just by searching. It's interesting to kind of look at this and ask, what does it mean for the AI to be good at math in this case? Because we have this sort of same guessing and checking problem, right? So in this case, frontier math is structured as hard questions, easy answers. So here's a problem. Okay, I'm sure that some people in this room can read this, but I can't. But the point is, at the end here, there is a question. There's sort of find blah-de-blah, right? The professors in the audience, of course, have already got the answer. But for the rest of us who don't understand this kind of mathematics, I will spoil this and say the answer apparently is 866. Incredible. But the nice thing about this is that we have, for frontier math at least, we have these kind of very small, compact integer answers. And that's very much by design, because that means that then we can solve this guessing and checking problem. So we can say, OK, here's a frontier math problem. Here's our math AI. We give this to our checker. And the frontier math AI comes up with some answer by some process you don't understand. And then what we have is a very, very simple way of checking that it got the answer right. So we just sort of say, hey, OK, is this actually the answer I wanted?
You can often sort of guess that something is true without really knowing whether it actually is true in your steps along the way, and in particular with these answers.
Yeah, that's correct, yeah.
So, it could be, hey, there's some deep theorem required to say that some step of this is actually producing the correct calculation. That actually isn't known by the audience.
Yeah, and in this case, so frontier math is supposed to be designed so that there's no other way to get the answer. Just for online, the question was sort of, this doesn't necessarily demonstrate competence or understanding. You could cheat, basically. There could be some way of getting the answer, which means you don't understand it. But in this case, frontier math is supposed to be designed to resist kind of those sort of attacks. But in point of fact, there have been cases where I think that the team decided that there were shortcuts that they didn't know were there. I think in aggregate, it's a fairly good kind of proxy, but it's certainly not perfect. Because especially for this, 866 is not that big a space of possible answers, I suppose. Oh, go ahead, yeah.
Maybe to fill in some of my sense with this, and I don't know if I was looking at frontier math or a different benchmark, this is kind of an enumerative combinatorics problem of sorts with finite fields. They use slightly different terms than that. What was it? Enumerative geometry over finite fields.
I knew there'd be some mathematicians there. That's great.
So it makes sense that even if you weren't using AI, having a computer crunch through a ton of cases would be helpful for this kind of problem. But it's not clear that methods that you would have, even aided by SAT solvers, would necessarily resolve this. So I think that's quite a bit more narrow than just saying math, the frontier of math, but also quite a bit more interesting than just saying, boring calculus.
Yeah, and I should also say that I don't think frontier math is intended to be, any individual question is intended to be representative of math, but they did work quite hard to try and cover as much of math as possible while maintaining this easy to check design. Now, okay, so the problem, basically this is the point. The problem is most math questions, most hard math questions actually require proofs, right? We can't just we don't have closed form answers. And the problem that we have here is that, well, a math proof, okay, so a math proof is a really good thing. This is a nice animation from Wikipedia. It's a thing where kind of we have like a structured argument, its individual step can be confirmed, and it has this really nice property that a proof is typically sort of like, it's sort of trustless, right? We don't have to like know who came up with it or believe that person is kind of good or fine or has good intentions. The proof itself is a separate artifact that we can check. And so this is a very nice thing to have if we can get to it. But the thing is that like human proofs are actually relatively hard to check in the way that we want. We can't write sort of a conditional statement that says, if blah, 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 unlike the normal way that people structure proofs. So like, for example, we have this theorem here. It's written in Lean syntax. I'll talk about Lean later. And so like, it basically just says that like, if you add 0 to a number, to a nat, then you'll end up with a nat. And so if we want to prove this, well, OK, there is like a kind of way to prove this in human mathematics that a mathematician would understand, I hope. It's let n be an arbitrary natural number. There's an induction process. You kind of like, OK, either you're in like the case where, we know this for kind of the smaller values or we don't, right? But this isn't really very easy for us to write like a highly trustworthy checker for this kind of proof. It's just hard to do that. And so human proofs are hard to check in this sense. And it's also true for like harder proofs. Like this is the very, very easy, straightforward. It's Fermat's last theorem, so it's not easy. But here's a theorem that we might want the AI to prove. Actually, we already Andrew Wiles already proved it, but we might want to kind of get the AI to prove similarly hard things, right? And so, okay, like the sort of AI says, great, wonderful, I found a proof, good news. And then it sort of like says, look at my kind of amazing PDF of 100 pages of like this sort of stuff here. Well, we can't very easily check this. It's just hard to kind of check this stuff. And it's, obviously like there's a very nice, sort of paper that kind of like goes into this in detail. But it's not really something that we can kind of give to a proof checker. And in fact, like in human terms, like even if you're someone like, like a real human mathematician, trust takes a lot of time. And so, Andrew Wiles kind of comes up with the Fermat's last theorem proof in, like 1993. And I think that there turned out to be some problems with the proof. And then by 1999, after having fixed some problems, the proof is broadly accepted, right? So this is sort of like a long process of like checking this. So if we were going to use our AI mathematician, we're going to run out of people to check the proofs quite quickly. We're not going to be able to scale mathematics if we're going to do it this way, no matter how nice it is. So yeah, there's quite a long gap between these 2 points. That said, mathematicians are using like AI as part of their processes, even without kind of doing like, in the sort of normal mathematics sort of a way. People have been working through these Erdős problems. The nice thing about this kind of talk is that like people kept on doing interesting things, and I thought, I'll stick that in the talk, right? So this was like Tuesday when I was writing the slide. Someone solved this kind of Erdős problem. I think this is like genuinely sort of feels like the moment where going by like the people I follow on Twitter at least, where some legitimate mathematicians were legitimately impressed by by this result. Previous Erdős problems, I think, have been more like things that maybe were understood somewhat in the literature, but this one feels like more like a novel result. So there's like the AIs are kind of producing these things, and they're writing them down in kind of like human mathematics. It's very interesting. Okay, and formalization underway. So okay. So if we want to use like mathematics as our kind of, if we want to use proof as like our workhorse for other kinds of things, we obviously can't do this in like this human proof kind of a way. We have to have some other way of dealing with it. And the way that we can do that is we can do kind of write down our proofs as code. We can write them down as Lean theorems, or like other interactive theorem provers are available. So like, here's a theorem as a bit of code. Well, this is one from earlier where we sort of say, okay, we'll add 0 to something. And then the human proof would be something like, we take n, it's an arbitrary natural number, we proceed by induction on n, and then we have a base case, which is n equals 0, And obviously, in that case, they're both 0 by definition. We have the inductive case, and so assume k plus 0 equals k. And then we have like the inductive kind of step as well. And we can write this down in code in Lean. Lean's very nice. So this is just a way of kind of saying that we have like a rigorous argument that follows the structure of the kind of human reasoning, but it's written down as a piece of code as well. So we have like we have a natural number. We do induction n with 0. Well, Ruffle says that it's basically sort of obvious. Or we have like we have the successor of k, and we have the induction hypothesis, and then we do some simplification. So this is kind of this is a really nice thing to be able to do, because now we have a way of writing down mathematical facts as kind of theorems. And like this is kind of part of this whole idea of like interactive theorem proving, which actually is like very old. It's like probably 1970s. And Lean is a fine tool, but in a lot of ways, what it is the culmination of a lot of other tools that have been working on this kind of idea. It's just that mathematics has made it much more viable than it was before. The nice features that we have are that when we have proofs written in an interactive theorem prover, we have a way of writing down our proof, and we have a way of checking it that's highly reliable, so it's auditable, that's legible. We can understand why it's correct. And we can use that as kind of the way to be sure that our proofs are correct. Oh, go ahead.
Has made it a lot easier than it was before?
I mean, AI has made it a lot easier than it was before.
Okay. But AI was doing this since the 70s.
Yeah, I mean, sort of like the current generation of neural AI seems different in, it's just its capabilities. But you're right, there's a long continuum about AI mathematics, of course. So like, here's an example. I mean, so this QR code is a link to like the Lean playground, so you can in fact follow along at home if you would like to do that. So you can sort of write this in Lean, and you can sort of step through the process that in a very nice way, you can sort of see the mathematics happening, see the proof actually happening. So, we can say, okay, well, let n be a natural number. Well, we know that n is a nat, and we've got a goal state at the bottom here saying n plus 0 equals n. That's what we want to get to. We can kind of break this down into the 0 case. And in that case, we say 0 plus 0 equals 0. This is quite an obvious fact. And then we also have the inductive case where we say, OK, well, we know as the induction hypothesis, k plus 0 equals k. And then at the bottom, we have the kind of goal states. And it's sort of fairly obvious why these two follow from each other. So Lean gives us a nice way of like dismantling mathematical facts and like putting them back together in a nice way. And then we can kind of prove this, have no more goals. The theorem is done. This is like a high sort of trustworthy state to be in. So, OK. So Lean proofs are mostly trustless. And this gives us a way of like actually kind of using the AI as a kind of source of truth without having to kind of, sort of like, parse all these complicated math PDFs or whatever. Right? We have our theorem. We have asked the math AI to kind of come up with something. And then we kind of hand it over to the checker, and the checker hands it over to Lean. And then Lean is the thing that actually finds out whether or not you got it right or not. This also is nice because often the math AIs make mistakes, or like the AIs make mistakes of all kinds. But then we also have like a really strong signal because you can say, OK, well, you got this wrong. Go back and like take a look at this again. And like intuitively, like these AIs are very reliable. They can be pushed to reliability, but like what you need is some way of it telling whether it's on the right track. And like this is a really powerful way of kind of pushing it into the right state. And we also see the AI starting to get good at Lean. So the AIs sort of like this is kind of a harder task. Well, it's sort of a different task from like doing mathematics. It's more like a coding task. And so it's harder in the sense that if you want to both prove Fermat's theorem and formalize it, that's two things to do. But it definitely also has its own kind of quality of difficulty, which is like it's just hard to kind of write Lean theorems sometimes. But we do see, in fact, the AI getting good at Lean. Here's like one bit of evidence. This is from March. So again, this is like hot off the presses. So this is, I think that SorryDB is basically was taken out of the it's from the kind of like Lean community. It's a bunch of like theorems they kind of grabbed. So a fairly kind of broad sort of spectrum of different theorems. And what we can see is like Claude Opus 4.5, if you try like one iteration, it does about 7.8%, which isn't that good. But it's like, pass it 2, it's like 15%. I think these are like, given the sort of range of difficulty, this is pretty respectable. And I think I think that anecdotally, we've seen like the AI going from being really terrible at theorem proving as of about 9 months ago to being quite good, to being respectable, and not really slowing down all that much. We see kind of momentum building for this. And I mean, another kind of good indicator is that the leading edge here is the sort of these, what we see sort of like these, I think these iterative ones are ones where basically they kind of, they do sort of like multiple rounds or something like that. And that's kind of, it does much better.
Sorry, quick question. But what happens between the first and the second round? They get some feedback or just...
Yeah, I think that's beyond what I've dug into on this paper. It's this is something that I found a couple of days ago. I just haven't had time. But yeah, I think pass at 1 is a kind of like pretty clean kind of question to think about. Yeah. And I mean, another sign that I think that the AIs are getting legitimately good at like proof and lean is that we are seeing like actual companies building their business models around it. And so we've seen a bunch of like stuff. This is from Leo DeMora's slide deck he did a little while ago. But these companies mentioned at the bottom, Harmonic, Axiom, Logical Intelligence, Math Inc., their business model is that they are building mathematical solvers, and they are building them targeting lean. And their theory is that this is going to be a very valuable technology for not just mathematics, but beyond mathematics. I mean, this is above my pay grade. So we have like these, but I mean, whether or not this is like a good business model or not, what we do see is that they are kind of building tools, and those tools are proving to be successful against the lean sort of targets. Oh, so yeah, this is kind of, I guess, like fair winds, sort of fair weather. Like, you know, we're seeing momentum in this direction. We're seeing like proofs getting cheaper, and we're seeing automated proofs getting cheaper, and we're seeing them get cheaper quite quickly. And so I think that, you know, there are, like, we're sort of like living in this strange, we live in this strange state now where we do not live in a world where like human mathematics has been replaced by the AIs. But we are seeing the trend lines keep on going up, and the AIs are getting significantly better step by step. And the end state of that is that like the AIs become very good at mathematics. They become very good at proving theorems. Yeah, go ahead.
Out of curiosity, I feel like there's at least 3 flavors of proof in this kind of work. One is I have sort of a leaf theorem, and it's fiddly, and I want to fill it in. Another is I'm somewhere in my proof development tree, and I want to, you know, break things down and fill it in, but it's fairly mechanical. I want the lemmas mostly to keep things manageable, legible. But another is I need to come up with a lemma and figure out the induction hypothesis. Do you have a sense for, across these benchmarks in these places where AIs are getting good at lean, what kinds of proofs people are doing with them?
On the math side, I think some of these are sort of, they require kind of modest amounts of like lemma discovery as well. Like I think that the Erdős one is like genuinely, if I understood right, required sort of actual like, you know, what you might say like creativity, abstraction discovery. I think that like it's really, I mean, I think you're making a great point. There's like on the one hand, there's sort of, you take like the 100-page Andrew Wiles FLT kind of paper, and you just sort of transliterate that into lean. That's like auto-formalization. And really there's sort of, in one way, there's no creativity there because like the paper gives you all of the structure that you need, right? On the other hand, there's like the totally kind of crazy idea that you could give just the top level theorem to the AI and then ask it to kind of like scaffold the entire interior structure of the proof and figure out all of the interior lemmas and all this kind of stuff. I think that that's kind of just a harder problem. Personally, I think that the AIs are on track to do that as well. I think it's quite likely that they will, for the same reason that they can do, the same reasons that they can do kind of like software engineering, they will be able to do that kind of, they can write internal functions, they can also write internal lemmas. But it is like an intellectually more demanding task, I agree. And so like maybe that's more like, do we expect mathematicians to be replaced as a category of like activity? Yeah. Anyway, so part of the purpose, I'm sort of saying this out loud, in 2 years' time, I'm sure that someone will come up to me and say, hey, you said proofs will be cheap, and this proof isn't solved yet. So I think it's good to kind of like, sort of say this out loud, in part because I think that this is like a part of the probability distribution, right? Like we don't know what is going to happen next in AI, but I think there is a world that we may live in where proofs end up being cheaper on quite short timelines. And in that case, we should think hard about what we would do if that was the case. And so this is like, I don't think you should take this as like, don't mortgage the house and bet on this. But it's definitely kind of part of the distribution.
Isn't a better question, which proofs will be cheap? Well, some already are, some maybe will never be, but the question is which ones will be cheap?
Well, so cheap prooftopia, that in my view is the AI is comprehensively, generically better than any human mathematician at everything, right? That is the kind of like claim I am making, right? And I think that like people probably don't agree, right? I think that's part of like the probability distribution we should have. Like I don't think that's implausible, and I think we should consider that as a possibility. And I think that sort of the analogy is sort of like math AI is like chess AI. Like there was a long time when humans were better than AIs at chess, and there was an era where the humans and the AIs were kind of comparable in chess, and now it's very obvious that no human can beat the best AIs at chess, right? The AI has become like comprehensively better at every kind of chess game. It will always beat even the best humans, and I think that there's those capability curves, they look pretty impressive. Like I don't think it's like crazy to think that that might be the world that we live in. But there are kind of like worlds where like the AIs just become like very good as assistants to human mathematicians, and that'll be the world for a while, I think. I think the evidence why you should think this, well, those AI capabilities keep on capabilitying. Proofs are a very good training signal. I think that's another thing is that like, we can tell whether we got the proof right. And like this, we can build data sets of these proofs. And I think a lot of these tasks are strongly analogous to software engineering, task solving, reasoning, things that the AIs are also kind of like improving on very quickly. And so if we see them getting better at like reasoning in general, task solving, software engineering, we probably will see them kind of get better at math. Okay. So so we solved math. Okay, we did math. I'm very sorry, I wrote that specifically to annoy people. So like suppose we have like really good AI, like AIs that do math. Well, in some sense, the question is sort of like math, what is it good for? Absolutely nothing. Is it like kind of like, is math more like chess, that when you have like really good math AIs, everyone's like, okay, well that was great, but like what does this change? Maybe it doesn't change that much. Or is it like we can use those for other things? Like I tend to think more the latter, that math is a huge deal, but like what are some concrete things we can use it for? Well, we definitely want these things, like some of these things. Like we want to kind of be able to oversee AI systems. We want the AI systems to be secure and correct. We want AI actions to be helpful and harmless, all this kind of stuff. So, and this is where it kind of comes back to me, like more in the formal verification tradition. Maybe we can use like proofs as a kind of oversight technology, as a way to kind of oversee what AIs are doing and to be sure that they give us what we want. This is an idea that I think some people have called like formal oversight. So the idea here is that like you have some problem description, you have some specification written in lean for what we want, and then we ask the AI, well, not a math AI, I suppose just an AI in general, we sort of say, hey, produce a solution, and then propose a solution and give me a proof that you actually meet the specification. And then we can sort of ask Lean to kind of check that it actually solved the problem that we wanted. So this is potentially like really nice because we can use Lean using a bunch of like very well-known PL techniques, the sort of thing that me and Zach and lots of other people have spent our careers on, to do things like memory safety, process isolation, encryption, these kinds of things, to represent like the functionality of things, like to say what, you got what you wanted, you are happy. This would be a very nice thing if we could do this when we're building systems. And we can encode these into kind of like Lean specifications. There's an asterisk there. I'll talk about that in a moment. So this is like a particularly nice thing because when we're sort of talking about oversight, like we might expect that as the AI gets cleverer, that it's more difficult to understand what it's doing. Not because it's malicious, but just because it's going to be doing, like, I don't know, your AI wants to do a sort of 600,000 line pull request, right? And maybe it's like that's the right logical step for it to take. But like you, with your tiny, wet meat human brain, cannot review a 600,000 line pull request reasonably. And so like as the AI gets more capable, it's going to be harder to understand what it does. But the good thing is that as it gets better, the AI is going to be more able to prove like specifications because it's going to become more mathematically capable. And so it becomes more viable to do sort of oversight using formal verification. So this is a kind of like oversight that kind of scales with like AI capabilities. There's sort of two things kind of the two signs go in the same direction, more or less. Okay, so this is like a nice idea, but there are several problems. And I'm now in my comfort zone, which is talking about problems. Problem number one, proof is famously very hard. So like, I've worked in formal verification for 20 years, and it's great, and I love it, and my heart is with formal verification, but like the industry is not very big, to be honest. And there have been some real successes, things like SEL4 and Hacklestar, amazing projects, lots of other things that have happened, lots of verification teams out there, but in aggregate, most of the world, nearly all of the world is not formally verified. And if you look at like these kinds of technologies, I think it becomes very obvious why this is the case. So here's an example from SEL4, which is a verified microkernel. And here we have like the SEL4 code is 8,500 lines of C, and the Isabelle proof is 165,000 lines. Like, that's rough. And like the other problem here is like when you change that C code, some of the SEL4 proofs have to change as well. This is a very unamenable kind of technology to use in a production environment. It's very expensive. And like for SEL4, it makes sense because SEL4 is like a critical security infrastructure, but it's very hard to do like a large, verifying the Linux kernel, for example, seems like it's not going to work, right? With these kinds of like ratios. And this is circa 2009. I think the current ratio is something like, I think it's about 1 million lines of like handwritten proof, which is like, it's a lot of people's time to build something of that scale. But now maybe we have the AIs. Maybe what we're saying is like proof used to be expensive. Yeah, go ahead.
Slightly tangential question on the last slide. Do you have any sense of why that is? And maybe not just in magnitude, but do you think there's like an asymptotic divergence between code and proof for any reason?
Well, why do I think there's so much proof? I think proof's just hard, right? It's just like, SEL4 is like a particularly difficult example because you're sort of trying to state a lot of deep security properties about the kernel, things like, process A and process B are sort of like not connected by, the information flows, things like that. But it is like just in general, like proof is like just, you have to be insanely detailed and it's very hard to automate and yeah, lots of things.
Proofs are always longer than theorems. And the self-void
okay, but are they a constant factor longer or?
I think it really depends on the theorem. And it depends on your idioms and like automation and all these kinds of things, yeah. Go ahead.
Yeah, I'm a freshman at the college, so my question might be stupid, but like, so as you have this library, so you claim that it's to be secure by giving out like a very comprehensive proof, but I mean, for cryptography, sometimes a comprehensive proof theorem doesn't mean it's actually secure, because you might have something like differential attacks that actually take advantage of other stuff, like not the algorithm itself, to attack that. So it could still be insecure.
Excellent question. That's about 2 slides in the future. So yeah. Maybe let me deal with that in one moment. Maybe proof only used to be hard. So like I think that like one reason explanation for. Oh, I'm sorry. Yeah.
Oh, I'm sorry. It's okay. I was wondering if you would still need to review the AI-generated proof code to make sure it hasn't done the lean equivalent of return true, always assume, like.
Yeah, I think that's the nice thing about lean is that it's sort of mostly there's like this distinction between like a theorem statement, which is like you're responsible for, and then the proof, and the proof is sort of it's checked by lean's kernel, and so it is sort of supposed to be. Again, wait a couple of slides and I'll get to this. But it's supposed to be that like there is no way for it to be wrong about claims that it makes in a proof, right? So it sort of gives you this, if you're talking about this in some ways, like, you have like a sort of statement of the theorem, which is like some small percentage of this, and then a large amount of this is just sort of like ephemeral. You shouldn't have to kind of review it. It's a little more complicated than that in point of fact, but that's kind of the aim. Anyway, so like historically, like this is how the world has looked. Like we've had like costs and benefits, where like projects kind of are good or bad, but depending on whether they kind of meet the kind of break-even line for how much they cost versus how much they benefit you. And for human written proofs, the kind of the sort of tiny habitable zone of like projects has been really tiny. There's almost no projects pencil out, and that's because they're just really expensive to do proofs. And so, like, a really nice thing is that maybe the AI-assisted proofs are going to kind of yank us across the kind of this line, and like a lot more proof technology will be like way, way more useful because we have these AIs that make them a lot cheaper. So problem 2, world modeling. This is where I'm going to talk about both of these issues. Like, world modeling is incredibly hard. And so if we think about the trust pipeline here, we're going to have like a piece of system code, which might be written in Rust, something like that. We turn it into a model, we have a specification, and then we hand it over to Lean. Well, the first thing is we're going to have some tool that takes our Rust code and like turns it into some model in Lean. And you're sort of assuming that this is like a library model is correct, your language semantics is correct, your hardware, your OS. I mean, another thing that you're trusting here that's like I'm talk about it in a moment, is also that you like stated like the properties you care about. So like, for example, your model might not include microarchitectural attacks, sort of meltdown inspector type things. So there's sort of like did you model the world correctly? And there's also like, as a side to the question, there's also like, does Lean actually do the reasoning correctly? And Lean is, I think, a pretty quality tool, and they've done as well as I think anybody else could have done. But still, it's a piece of human-written software. Maybe eventually it'll be an AI-written software. And it's got a logical core and a runtime and things like this. And in fact, we just this week, we had an example of like a buffer overflow in the Lean runtime. Okay, this was found by Claude, by the way. So this is basically like kind of like AI red teaming of the Lean runtime. It's a nice blog post. And so so Lean is like quite trustworthy, but like nothing in this world is perfect. And in some sense, this is just an engineering problem, right? Some of it's just an engineering problem. Like, do you have a really good way of getting Rust code into Lean? Do you have a really kind of good story about how you've audited Lean? These are just engineering problems, but the gap is kind of pretty significant. Okay, now this is the like genuine end boss kind of problem, which is specification is very, very, very hard. And the problem here is basically like, okay, so when I sort of said, okay, some specification, well, where did this thing come from, right? Who wrote that? Well, you could get the AI to write it, but then you just kind of, the AI is marking its own homework, right? You don't want that, right? But you sort of also, you're assuming that you understand what the spec means and that you understand what you want, which might be even harder in some ways. And so where do these specifications come from is the kind of really important question. Like, I think one way to think about this is, like, okay, here's the SEL4 code. Here's the proof. Well, here's the spec, right? Which is like 5,000 lines of code, right? And so you're like, okay, great. Well, now I I don't have to read the 9,000 lines of C code. I can just read the 5,000 lines of specification instead. And like, this is clearly like a big problem. Like, we really want like the AI to kind of be able to help us in some ways, but we can't trust the AI as a root of trust. This, we're getting a lot more, we're getting some leverage on the problem. I think SCL4 is a particularly extreme example, but I don't think it's kind of like totally unrepresentative. Yeah, go ahead.
Apologies if you were going to say this, but not apologies if you disagreed. It seems like you're also, for people who haven't done this kind of work, the way the humans get those 4.9K lines of specification right or more right or useful is to work on the proof. That's what we do, right? And then, oh, it was too easy. Oh, that's because I gave a vacuous statement, right? Oh, it's too hard. Oh, that's because it's not actually true of the code. And back we go. So if we are going to be the ones specifying and we're not going to be the ones proving, how will we work on it?
I think that's a great question, and I think it's sort of, the idea of, having tools that could just do the proof, like those tools don't, that capability does not exist yet, right? So in some sense, like, we are all just figuring this out, like, and so I certainly hope that nobody is coming away from thinking like that I have solved this problem. What I'm saying is like, these tools are going to be super useful, and like if we can find ways to like use specifications as drivers for like assurance, then that will be amazing. But there's like incredible challenges. Like, this is totally not the way that people have worked on these big proofs in the past, and I think that's going to be just a workflow question as well. Some other things about specifications, I suppose, like ideally mathematical specifications are like clean and stable and agreed by everybody and easy to reason about. And when you look at the history of these formal methods projects, I've said this in other talks, but like the big projects all fit this pattern. And like, you have crypto libraries and operating systems and compilers and cloud services and things, right? This is a big part of what we care about. But also, in some ways, these are like the kind of plumpest cherries on the tree. Like, most things are not very specifiable in this way. Like, most of them have like messy and fuzzy specifications. And I think in some ways, like, we shouldn't overgeneralize from just this. I think there's still probably quite a lot of things that are like too big, have some of this nature, but are just too big to deal with right now that we could deal with. But I don't think we could, like, if we sort of think about something like, Mike earlier was asking me about like Word, like what's the formal specification for Microsoft Word? Like, what's the formal specification for Chrome, right? These are both like really important pieces of software that we want them to be correct. But I don't think there's like a theorem that says, okay, well, this is what a Chrome is. It's like, how do we specify that? That seems hard. And the world in general is like full of specifications, but it's very non-formal. So you have RFCs and like things that look more like actual specs. But you often have like PowerPoint decks. I've read more than one PowerPoint deck than I ask, well, where's the real spec? And they're like, no, that's it. And I'm like, oh, damn, okay. And like often another thing that actually happens is like you often have the code, which is the code itself is the spec. So what is GCC supposed to do? Well, it's what GCC currently does, right? This is like not, the world is just, people just use a lot of tools for like saying what they mean, and like it's hard to come up with like small definitions. We worked on PDF on the SafeDocs project for DARPA, and like what we found was that like PDF has a nice specification. It's written by the PDF Association, and none of the implementations do what the specification says they should do. They've all had this sort of funny like relationship where they're kind of like, there's kind of a core where it all makes sense, and then there's these fringe cases. And I sort of feel like, I sort of stared into the abyss too much, and then I sort of realized that like everything's very hard to specify, and it's unclear what we do about that. Another thing is like, how do we get the AIs to help us to get the specifications right? Like, that's going to be necessary if we wanted to use specifications this way. Okay. So I think that's like, I'm going to sort of just talk, kind of close a little bit. But like, I think the point is like, there are like, we are getting kind of like to a world where like AI is going to kind of solve a lot of the problems that we thought we had with proof. And there are still going to be some really big problems to solve. And like a lot of these problems, I would say this, I suppose, they look like kind of formal methods PL type problems. A lot of them look like kind of usability or kind of like, they look like kind of oversight problems. They look like trust problems. And I think that we should kind of like make sure that we kind of focus on those and like put effort into them. So like this is the situation that we might be in. We have these large uninterpretable systems and the AI kind of builds them for us. Well, a nice world would be you could say, okay, well, can you prove this is safe? And the AI is like, oh yeah, sorry about that. Yeah, of course, here's my proof, right? And you're like, oh, okay, great, okay, let's keep going. This would be a very nice world to live in. But I think there's quite a lot to do before we could get to that world. And there's quite a lot of hard problems to solve. So I think that some of the missing pieces are like, in the Lean pipeline, Lean is amazing and it's moving quicker than I have ever seen like a formal methods project go. But there is still a large missing bit. There are a lot of missing pieces in the infrastructure. If you are enthusiastic about building tools, I think building things in Lean is very good. Is a very good idea. I am a proponent of the Lean theory of everything. Like everything, you should just build all your formal things in Lean and like port all your other things to Lean. But I think that we're still missing, if we want to kind of hit some real thing, we're still missing quite a lot of the pieces that we would need to do that. And then I think that the big thing that if you are an ambitious, like smart person, and you're looking for like the thing that will not be solved by AI getting better, like specification technology, I think is the thing. I think that's the place that we need like a large amount of kind of deep, kind of thoughtful work to kind of build the tools that will be potentially useful for kind of the future. One closing thing is I sort of wanted to pitch you all on my kind of like insanely hard thing that I would like to do, right? So I would really like a sort of verified agent like containment system, right? What you have at the top is you have like an AI agent. It has a permission system. That's like kind of like goes through a Docker container. That goes through this OCI layer, it goes to the operating system calls, it goes through the Linux kernel, and it goes to the hardware, and we verify everything, right? This is, I told someone earlier this day, and like, it's good to see them being like, this is not a possible project. But like, I don't know. I think like, suppose we have like agents that are just good at proof. Maybe we could sort of imagine what we're doing this kind of thing, like something as kind of crazy as this. But I think it means we have to ask, like, well, what's missing? And what's missing is, like, we would need, like, to be able to deal with a lot of real system code. We would need to be able to kind of, like, elicit specifications at the Docker level, at the operating system kernel level, internal kernel interfaces. Like, all of these things are things where we would need AI assistance pervasively. We don't have those tools today. We really need to build them. So, yeah, I think proofs are going to be cheap. And I think proof tech is very useful. And it's time to think big, and I think there's a lot to do. Thank you.
Okay, everybody, I think we have time for some questions. Pedro?
So you talked a lot about verifying AI proofs, but I wonder if you're overfitting to the current state of AI, because AI proofs shouldn't need verifying. AI should be able to produce proofs that don't need any more verification than a compiler output.
Yeah, you mean like the AI sort of is like it's so trustworthy that it always gets the proof right and we never have to doubt it.
There's a big search process with all the machine learning and blah 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 for the proof, but the proof that it produces, every step of it, is guaranteed to be correct. There's absolutely no reason that shouldn't happen.
Yeah, I mean, I think part of it is just like audit, I suppose. Like, so it might be that the AI is very reliable, but having like a proof checker like Lean is very nice because then we can look at the kind of root of trust and it doesn't rely on the AI itself. So it's sort of like separate like root of trust. But I mean, I think it's totally plausible that we'd end up with AIs that are so good that they essentially never make mistakes. I mean, that would be a wonderful world to live in as well. I don't know if I fully believe that that's going to happen.
Be able to prove something.
Right.
In many cases, they won't be able to prove it. But if they give you a proof, it's a proof.
Yeah, I mean that could be the case. I mean, I think it's. I think that this is like in one way like this vision is kind of like a pessimistic vision. It's a bit like kind of the sort of AI control idea that what happens if the AI remains kind of like unreliable but powerful. And I think that's possible. But maybe we live in a world where the AI is very reliable and very powerful. That's certainly possible.
Yeah, thanks so much for coming to speak with us today. I really enjoyed the presentation. In my mind, and one outcome of what your talk said is, hey, we need to be teaching more people TLA plus, or I don't know, Forge, Alloy, Lean, whatever combo you need there. And it used to be the case that you needed a PhD in that thing to write that kind of code. And now we're seeing undergrad classes pop up and kind of Lean being democratized across math. I'm curious, in your perspective at Galois, like how are you training people to use these kinds of tools? What does the learning curve look like at the company? And are there learnings that we should have at UW about how we should be teaching people about specification, modeling, formal verification, all that kind of stuff?
Yeah, I think that's a great question. We were just talking about this over lunch. Like, what does the kind of curriculum look like for this? So I mean, the way I've learned to use these tools is really just by using them. I think it's very hard to sort of give like durable advice, because what Claude is like today is not what Claude was like 6 months ago, and it's not what it was like, really not what it was like a year ago. I would say that like very good. I think that figuring out like how we should like teach people to use these tools, and also like, like I have a kind of gut sense like when a theorem is nonsense, but that sort of gut sense is not a very portable thing, right? I don't know how to kind of teach someone that quickly, and I think if you're thinking about these questions, I would recommend like, the space is wide open. I would use the tools and see what works, and then see how, you may be the first person to ask that question or work on that problem. And this is very exciting, but I don't really have much more advice beyond just kind of pick the tool up and hit things with them.
So your talk really resonated with me because I work on very large, very poorly specified legacy systems that need to be maintained for a really long time. And what we've been getting is a lot of people submitting these very large AI PRs. And they can be verified because we have good tests, and we know that they pass existing tests against an existing implementation, so the new Rust implementation is correct. But we still spend a significant amount of time reviewing them to make sure that they're maintainable and more qualitatively correct in a way that, they use good naming conventions and they're written in a way that is maintainable. So is there a way to use these proofs to verify the maintainability and the more qualitative aspects of the art of coding rather than the science of is it actually just correct?
Yeah, I mean, I think there's like this interesting dichotomy between sort of like, do you see like a sort of piece of code as like a sort of disposable thing? It's just like, it's the inside, it's the filling in the sandwich, right? Or do you care that it's like nicely structured? And so I think the AI is often, I think it's like, the proof tools that we have today are sort of, they're not really very oriented towards like code quality, right? Often it's the case that like provable code is reasonably nicely written because it just makes it easier to think through. I think it's sort of I think having more rigorous ways to like evaluate whether or not something is going to be sort of maintainable, idiomatic, is really interesting, and I don't know how to kind of solve that either. That also seems like it's a kind of spec problem in a sense, because like, can you read the code and understand it? Is like a sort of, can you elicit what it means from like reading the code? Yeah, I think it's again, very interesting unknown thing.
Thank you. Great presentation, actually. Very inspiring. But I still carry that question. So basically, if you're proving a certain algorithm that is like logically good, doesn't really mean that it's secure, right? Like I talked about, like timing and glitching, power attacks, all those kind of engineering techniques. So for your company like Galois, yeah, how do you guys actually process those or like do those audits in the industry?
Yeah, I think that this is kind of, this is the sort of inherent trade-off. Like, I gave a talk a while back where I sort of said, like, you shouldn't say when you formally verify something there are no bugs in the system, because like you're making assumptions. Like, for example, you're assuming no timing channels, or you're assuming no kind of whatever, and those are kind of modeling assumptions. Or you're assuming your libraries are correct. There's always going to be a sort of interface. I think that trying to like sort of communicate with the person you're doing the work for, like, well, these are the assumptions we're operating under. These are the consequences of these assumptions. So we can rule out bugs with reasonable confidence within this kind of area, but like we don't say anything at all about like the timing characteristics, for example. I think that's kind of a good practice when you're trying to do this sort of work. it is like, it's sort of the thing that's very hard about this, I suppose, is that you have to make some assumptions to make it possible to do this sort of like verification. But the bugs are probably in the area you didn't verify. Like, in the case of the lean bug that I pointed to, the bug was in the runtime, which is an unverified bit of the lean kernel. And so wherever you kind of put your boundary, there'll be things outside of the boundary that you don't deal with, and you've got to have some other way of dealing with that. So you got to kind of go in knowing what you're getting. So I think it's like, again, like a hard thing to kind of deal with. It's like part of the specification problem, basically.
One more.
Very interesting. I was wondering, what are the limits of this class of proof methods, proof techniques? In particular, can it deal with algorithms that handle uncertain input, algorithms that are randomized? Like, it doesn't seem to me plausible that one would be able to prove that a face recognition algorithm is correct. So, where are the limits of these formal methods? So that's one question. Second question, about the first part of your talk, you said that math proofs may become easy. I'm curious, what about the theorems? Somebody has to come up with the theorems.
Yeah, I think on the first question, I think you're right. Like, there are lots of things where, if we say like, oh, our facial recognition algorithm is correct, well, what does correct mean? It's like, well, we don't have like a mathematical definition of what the human face is. That's kind of the reason we need these kind of data science algorithms, right? I suppose you might be able to say that like my algorithm doesn't leak data in the way that I don't want, or my algorithm implements like the kind of like, there's a definition of what the algorithm should be, and the real code does exactly what the algorithm claims. But there's going to be, like the world's, if we're trying to verify a self-driving car, well, how do you specify that it never crashes? Well, in that case, you'd need a model of the entire world, of like all the situations it could possibly operate in. And that's like not a thing that we can really do. So it's sort of more like, is there a kind of crisp way of specifying the thing that we want? That's still a big category of things that we might want, but it's limited. It's like, you're never going to get rid of like what people call like V and V, kind of like, validation and verification. Like the validation is not going to go away. So the second question you're asking about, like, where do the theorems come from? Yeah, this is like, I mean, well, why do people find, why do we want answers to the, the sort of Collat's conjecture, right? I mean, it's not like the AI can want that, right? It's like we want that. But like that's sort of a human process of like desiring or wanting, right? Which has to come from us, I think. I could definitely imagine that, suppose that like the AIs are very good, that they might do sort of like, they might sort of say, okay, well, here's a bunch of interesting theorems that I found. Do you care about these ones? That's kind of would be a useful thing potentially as a mathematician. But I also think that like a good reason to, when I use the AI, I use it to build projects I care about, and like the reason I do them is because I care about them, right? That's going to come from like humans, I think.
Okay, let's thank Mike again